All right, welcome. This is a recording to cover the material that I had intended on giving you on this morning. And we had another glitch with As You Learn, and the Zoom, it turned out, didn't work out either. So listen, I'm going to go ahead and get right into the material. And I want to remind you, so some of you that came up, some of what I'm going to say is a repeat, but stay with me because there's a couple of things in here that are new, and it will be part of the challenge, okay? It's part of the moment. And so I ask you to stay with it, and let's get going on this. So I want to remind you from the beginning. Let's go over, we're moving into section 1.4. And the first thing that's mentioned in the title is it's talking about trig functions, limits related to trig functions and stuff. And there's an identity that we're going to be building toward. I want to just do a real quick review of remember the trig function, where trig comes from in that type of scenario. So I want to go to the iPad and go from there, all right? So what I want to do is, I noticed that I can't show my face. Somehow my video on the camera is not working on the computer. So I'm not able to get that from you, to you. So you can't see my face, so to speak. But here it is. Here's the situation. I talked about this earlier, that trigonometry. Remember what the word trig is based on. The first three letters are tri. The right triangle is what the right triangle trig is what a lot of this stuff is that we will be talking about has to do with. There's other types of trig, I mean, that are based on not right angles, but they're triangle trigs is the idea of it. And the main situation is remember what SOHCAHTOA stands for. Remember what we've got there. We've got the SOHCAHTOA. The S is for sine, the C is for cosine, and the T is for tangent. So determining the sine of a function is really dealing with a triangle that has to do with a side opposite over the hypotenuse. And the cosine is adjacent over hypotenuse. And the tangent is opposite over adjacent. And when we're talking about triangles, I'm going to go ahead and draw like approximately a 45-degree angle. That's not right on, but that's about what we're talking about. And the angle, the base part of the triangle, the base part of the angle is down here on the x-axis. So this angle right here, this angle is the angle that's being referred to here. And this, if theta is a common used in the trig function, so to speak. You can do a whole bunch of different stuff. And we're going to down the page, you can see we got cosine of x, and there's different variables that can happen. So just make sure you stay consistent. And if I ever switch midstream or something, know that there's a correct way to do it. You stay with what you started with. Cosine of theta. So one of the things I want to point out here is that this angle, the triangle that they're talking about, is the triangle that's formed with the angle of concern being down in that left-hand corner there. It is a right triangle is what we're talking about. And the length of the sides are pretty fixed in this situation. So the idea is that the unit circle is what it's based on, with a radius of equal to 1. It'll work with other circles too, but when you've got a radius of equal to 1, it makes it a really easier thing to work with. So notice on a 45-degree angle, when we've got a 45-degree angle, this side here and this side here are going to be exactly the same, because 45, 45, 90 triangles happen in there. 45, 45, 90 is the angle. So as a result, the two sides, the x and the y coordinates of this point are the same. And if you recall, when you work with if you set one side equal to x and the other side equal to y, and then you change them, because they're the same, you could change them both to x. And you end up, if you solve for x, remember on the unit circle, when you got the x there, that ends up being the square root of 2 over 2 and the square root of 2 over 2. Both of the length of those sides are the x coordinate, notice, is called the cosine up here, and the y is considered the sine. All right? The x coordinate and y coordinate in that sort of fashion. So this is the same. Another way of writing this would be cosine theta, sine theta. So all around the unit circle, Cosine is the x value, sine is the y. And so what I want to make a point of, so notice this, that therefore, it would turn out that the length of this side right here is the square root of 2 over 2. The y value, you know, this length of this side is square root of 2 over 2. And the length of this side turns out to be square root of 2 over 2. And that fits. And if you remember always that sine squared theta plus cosine squared theta is always equal to 1. Based on the Pythagorean theorem, we got a right triangle, a squared plus b squared equals c squared. And if x is the cosine and y is the sine, then cosine squared plus sine squared equals 1. That's the scenario, that's an identity you'll need to have burned in and know that that's true. You're using that in a variety of different ways. But the key point I want to make here is this. Let's review what the sine and the cosine graph look like. All right. So one of the key points I'm talking about here is that if, and one thing I want to make note of also is radian measure. Degree measure, usually when we come into talking calculus, most of the things in this text are going to be radian measure. Most of life circumstances are going to be radian measure. Even though, you know, we grew up with what's a 45-degree angle, a 90-degree angle, and that kind of stuff, the mathematics typically is going to be in radian measure. So the idea is this: at 0 degrees, remember this side, between the origin and 1, 0 here, is the base of the angle. And that is where 0 degrees happens. And notice in radians, that also corresponds, so that's 0 degrees. And that's also 0 radians. That would be called 0 radians. So 0 degrees is 0 radians. 90 degrees, you know, goes straight up. The 90-degree angle is going straight up. So this is 90 degrees. And that is, notice what this is, if, and I'll talk about this in a second. So if you add 2 of those, that's 180 degrees over here. All right, notice this. Remember what a radian is. That's 45. A radian is, take the length of this radius and swing it up and put it on the arc of this circle. And it would put it up right about here. You know, something like that? This is 1 radian. What's the radius on the circle? And one of the, okay, so 2 of them would put it up here, right? Add another one. 3 of them put it about here. So this is 2 radians. This is 3 radians. And it turns out that a little more than 3, 3.14 yada yada, turns out to be the length of this side right here. And 3.14 yada yada, the decimal going forever, does correspond to pi. So this is also pi. Half of that is pi over 2, right? 45-degree angle back there would have been half of that, which is pi over 4, et cetera, et cetera. Now, if you add another 90, 270 degrees, notice that that's adding another pi over 2. So that's pi over 2, 1 pi over 2, 2 pi over 2. We've got 3 pi over 2 down here. And then we've got 4 pi over 2, which is 2 pi. So 360 degrees is 2 pi radians. All right? So I want to make sure that's clear. And now let's look at this. So the values, I'm going to put these in here to make a quick reminder about how you can determine what the graph looks like, sine and cosine. Sine function, remember, sine is the y value. Sine is y. Sine is the y. Up here at pi over 2, the y value is 1. And at 90 degrees, the y value is 0. 180, excuse, oh, sorry. At 0, yes, at 90 degrees, the sine value is 1. Okay, so at 0 degrees, pardon. The y value is 0. We're right here. At 0 degrees, we're right there. It's 0. At 90 degrees, we're up here. I got thrown off there. Just pardon me. 90 degrees, we're up here, and the y value is 1. 180 degrees, we're back to 0. At 270, we're at, or 3 pi over 2. This is pi over 2. This is pi. This is 3 pi over 2, and this is 2 pi. Okay, 0, 1, and now the y value down here is -1, and the y value up here again is 0. All right, let's do the x value. cosine. X is 1 at 0 degrees, 0 at 90 degrees, at pi over 2, negative 1 at pi. And then you go to 3 pi over 2, and the x value is at 0. And at 2 pi, back up at 0 degrees or 360 degrees, the x is equal to 1. The cosine is equal to 1. So now we're going to make a graph, general plot of this. So let's do the sine function first. We've got 0 degrees, we're at 0. At pi over 2, we're at 1. At pi, we're at 0 again. At 3 pi over 2, we're at negative 1. And at 2 pi, we're back up to 0. And the graph, remember, it doesn't stop. It's not 2 pi wide. The graph goes on forever, okay? But the situation is that we've got this curve that looks like that. And it continues on, you know, it goes on and on and on forever in both directions. But it starts at 0 degrees. It starts there at 0, which is, we're going to call the midline. Okay, the midline, halfway between the top and the bottom, halfway between 1 and negative 1. Now let's look at the cosine. Cosine, at 0 degrees, we are at 0 radians, we are at 1, off the midline. At pi over 2, we're at 0. At pi, we're at negative 1. At 3 pi over 2, we're at 0. And at 2 pi, we're back up to 1. All right, so we end up, we've got the curve going here. Okay, and it looks like that. And from 0 to 2 pi at one full cycle, we don't run the circuit. Notice cosine does not start on the midline. Sine starts on the midline, the halfway point between the top and the bottom. Cosine, positive cosine, starts up at 1. Okay, it starts up and above, off of the midline. That's the key point to be made there. Now, what I want to lead toward is this, the identity that I want you to work with. We're going to be working with just a little bit. A couple of key ones that show up. The main idea is at 0. So the limit as, I want to use theta. I'll tell you what, I'm using x down here. I'm going to go to x, okay? The limit as x goes to 0 of sine of x, okay? What is the value as sine, if you come in from the right, or you come in from the right, or you come in from the left, you're going to 0, right? And the limit as x goes to 0 of cosine x, notice what's happening. You come in from the right, you come in from the left, it's approaching 1 as x goes to 0. All right, now a key one I want to point out here is this, and these are some problems in sapling that are going to require this of you. This is the identity that I want to point out. The limit as x goes to 0 of sine of x over x equals 1. All right, well, equals 1. Now, sine of x over x, as x goes to 0, that means sine of x, you get 0 on top and you get 0 on the bottom. Therefore, you've got this thing, and a little later on when we get into L'Hopital's rule, that'll give us a little trick on how we can affect this in a way and know the answer kind of quickly. But in the meantime, we got challenge of this situation. We've got a 0 in the denominator, and that's not legal. So what we've got to do, what I'm going to do is I'm going to go to sapling here. I'm going to go to sapling on the computer here. And notice this. Here's sine of x over x. All right. Now, without going through a proof of it, we could use some combination of ways to do it. But what I'm going to do is just verify, have it, make sure you see clearly that this is the graph of sine of x over x, right here. And the question is, notice what the limit is going to. Limit as x approaches 0. Where it is, it's right up here. So it appears to be that it is at 1. When you get to 0, it's undefined because it causes the denominator to be 0. Notice the hole up there. It's got a hole up in this circle there. All right, you got it. But the limit, because you're coming to from the right and from the left to the same place, the limit is equal to 1. That function. All right, so the graph in general. I'm going to go back to my iPad now. Look at this, if you would. Let's go back to the iPad. And when you, I made a quick sketch here uh, of the graph of x, sine x over x, right down here, okay? And it's a kind of a, it's not a real strong graph, but it's in approximately what that graph was. With the idea that as you're coming in from the left and you're coming in from the right, the limit as x goes to 0. Problems is now you come to a problem. Notice what happens here. This value and this value, the value of the denominator and the value that you're taking the sine of are the same. So when those are the same, the limit as x goes to 0, this function goes to 1. We got evidence of it seen on the graph there. Now look at this problem that's given here. And there's a couple given in sapling that are similar to this. I want you to see this. The idea is, okay, now notice the thing you're taking the derivative of, I mean the sine of, the thing you're taking the sine of is not x. The denominator is x. But the sine, what you're taking the sine of is 3x, not the same. Notice what has to happen back in the original function. They both have to be the same. Now, one instinct might be that you could just multiply that sine by that number by 1/3, okay? And if you multiply the top by 1/3, well, you're multiplying the angle that is inside that thing. That is not a linear function, okay? That's a curvy function, sine. So the number inside there, if you multiply it by inside like that, by the angle, and then by the outside, by a linear thing that's on the denominator, the answer is going to go all over the place. So you can't do that. But if I want to make that denominator equal to 3, and I multiply by 3 to get it to be 3x down there, I still have to multiply the top by 3, but it's going to be on the outside of the function, not the sine of that value. All right? So we end up with, notice what that is. So this is the limit as x goes to 0 of 3 times the sine of 3x over 3x. Now we've got these two values being the same. All right? And remember that if you take the limit of a constant times a function, it's the same as the constant times the limit of the function. So this is the same as this. I've got the 3 out front this time, and I've got this now. And what they do in the text is, we've got 3x is what we're working with, but to make the visual clear that that was the same thing, they replace it with t or something like that. So you end up with sine t over t. Well, there's section 1.4, but what I want is I want the slideshow. Okay, I think this is it, right? Yeah, slides 1.4 and 1.5. Okay, so I believe that this is now the slides for 1.4, and you can see them, yes? I'm verifying that you can see that. Okay, so what I want to point to is this. Now, I want you to recognize that this is where we're moving. Let's go in this section 1.4, okay? The section 1.4 slides. Check this out now. Use the squeeze theorem. I'm going to step past that right now. That was the way initially they showed that. I used the graph to demonstrate the sine of x over x, limit as x goes to 0. They use the squeeze function. We'll talk about the squeeze function theorem later, but we want to talk about limits involving trig functions, where are trig functions continuous, and where are exponential and logarithmic functions continuous, okay? That's the key thing. And now, these are the things I put up on the iPad. This is by definition, the sine x, when sine of 0 is 0. And the cosine of 0 is 1. So the limit as x goes to 0 is 1. The limit as x goes to 0 is 0. Now down here, the one we just worked with is the limit as theta goes to 0 of sine theta over theta. That is 1 in measure in radians. So this is a new identity we're going to work with. We're going to pass on this one right now, not worry about the second one dealing with cosine. We're working with this right now. And I want you to be able to realize that sometimes using an identity can benefit you. And they use it in one of the proofs that we'll talk about in just a little bit. But this is the one I want you to get familiar with, okay, and utilize in fair game on assessments coming up. So let's look at this situation right here. This is the same thing we did on the iPad. So we had 2 pi, the sine of 2 pi over, sine of 2 theta over theta. Limit as theta goes to 0 of the sine of 2 theta over theta. So if you multiply the bottom by 2, you don't multiply inside here. You got to multiply the 2 by out front, okay? And we realize what that is, and what they're showing here is they're showing that you get this t is their replacement. You can see that it's, and they make it t instead of theta. But the idea is these two are the same, is the key point. And then they bring the 2 out front, and you get this. And the limit of this as t goes to 0 is equal to 1. So 2 times 1 is 2. All right. Now they do a second problem here, a little more complicated. And the idea is, check this one out. Right, make note of this, you might want to, because I might ask you something a little more complicated than just a single step like this. But you know, look at this. The idea here is that they've got the situation of sine of 3 theta over the sine of 4 theta. The limit as theta goes to 0 of these two. And notice what the plan is here. This isn't sine of theta, sine of some value over just a number. It's another sign. So what they do to solve this problem is they convert the top to be over a theta and the bottom to be over a theta. And then they affect the top and bottom in such a way that both of these will become the value you can work with, and you use the limit on, you know, get these two to be the same, get these two to be the same. And as a result, you got the situation of being able to use that identity. So in this case, multiply the bottom by 3, they had to multiply the top by 3 outside. Then they had to multiply bottom by 4 to get 4 theta. And then they had to multiply the top by 4. So you end up with, here's your sine of 4 theta over 4 theta, that's 1. So you got 4 times 1. And up here you've got 3 times 1. So as a result, you end up with 3 divided by 4. The limit as theta goes to 0, it's like bringing the 3 out front, bringing the 4 out front. Well, they're not doing that anymore. They just do the shortcut because you know the answer. So now, and you don't have to do the whole thing, bring the 3 out front and show me that, bring the 4 out front. You can recognize that this is 3. This is 3 times 1. And this is 4 times 1. That is equal to 3 over 4. Okay? So I want you to see that and be confident with it. The other thing I wanted to talk about was, one thing that was mentioned was the continuity of trig functions. Earlier I had mentioned that, remember, it doesn't stop at 2 pi and start at 0. It goes forever to the left and goes forever to the right, both the sine and cosine function. They're continuous for all real numbers everywhere. Those functions go on forever. Both sine and cosine are continuous everywhere, okay, for all values. Now, when you get to the tan function, which is defined by sine over cosine, which is opposite over adjacent, remember, tan function, you've got cosine in the denominator. Anywhere that the cosine is 0 is causing this to be undefined. And as a result, and that happens where? Where is the cosine equal to 0? Where is the cosine equal to 0? Whoops, cosine theta equals 0. Where is x equal to 0? X is equal to 0 here, and x is equal to 0 here. So x is equal to 0 at 90 degrees at pi over 2. And it's then you go around to 270 down here, x is equal to 0 here. Or if you come back this way, you know, you could say negative pi over 2. This is negative pi over 2. You could also, you know, call that negative pi over 2 radians. Takes you down here just as well. Same as this is 3 pi over 2 or negative pi over 2. But anyway, top and bottom of the circle, x is 0 when you're on the y-axis. So every time you hit that, it's equal to 0. So at pi over 2 and at negative pi over 2, you've got the asymptotes. So let's get back to the diagram that we had on our the screen here. Notice this. Positive pi over 2, there's an asymptote. Doesn't happen. At 0 degrees, cosine is, you know, is not 0. At negative pi over 2, down at 3 pi over 2 or 270 degrees, Negative pi over 2, remember, x is 0, cosine is 0. So you've got a vertical asymptote there. And that's why you've got this repeating tan. This is over the next right beside it, and it's repeating out there forever with odd numbered pi over 2s, odd number times pi over 2 radians is going to be 0 every time. So tan is continuous for all real numbers except odd multiples of pi over 2. That's the idea of that. One other thing I want to mention, if you got questions on that, let me know. Now for exponential and logarithmic functions. Remember, e to the x, what they've got drawn here is the function e to the x. Notice what e to the 0 is. When x is equal to 0, what do you get? E to the 0, anything to the 0 power is 1. So this is at 1, right? And then you get over here to 1. There's x equal to 1. You're up here at e. So e to the 1 is e. Remember what e is. It's a number. It's kind of similar to pi. But the idea is it's 2.7, yada, yada, yada. And it's a matter of making sure you remember it is a number. E is not a variable. But the idea is that e to the x, e to the 0 is 1. E to the 1 is e. So this is e, which is 2, 1, 1, 2.7, yada, yada, somewhere up here. At 1, it's up here. Okay? Now remember this, that's for the exponential function is typically e to the x. Remember, if you have log, remember that's 10 to the x. We're going to be working with e to the x mostly. Exponential functions usually going to be e to the x. But if you've got 10 to the x, what does that give you? If f of x equals 10 to the x, you plug in 0 for x, you got 10 to the 0, which is 1. But when you get over here to 1, you go 10 to the 1, so you're way up here. This is, you're way up here. This is 5, so it's twice as far. When you go over to 1, you're way up here. So it's just a lot steeper. It climbs faster, okay? So exponential function looks like this, whether it's e or 10. Log is dealing with 10, and e is dealing with e. But here's the graph is tended to look like this. Notice this, never below the x-axis. And now the log function, if you notice, the exponential function, if it's e to the x or 10 to the x, it looks like this. The log function now is saying log of something, which is, remember, that's got to do with when you're trying to get huge numbers and it converts it down to simpler numbers, so to speak. But the log, log or ln function looks like this. It can never be negative. X can never be negative. The log can be negative. The ln can be negative. But the situation is the x value cannot be negative because there is no value. You can't take e to, there is no power you can put on e that will give you a negative value. So part of the situation is the x will never be 0. I'm negative. It can never be less than 0. We do have y values. It can be negative. We'll be talking about that more as we go. But the graph looks like this. It goes down as at, notice where this value is, at the log function. And